So today is a summary of part 1. Tomorrow is the exam. And my idea would be that, I don't know, I give... Any questions? So my idea would be that for the first part, the first 45 minutes till the break, I give a summary of stuff, another high-level view of the content we had so far, connect the dots as much as possible again. And then the second part would be about your questions, clarifications. Yeah? Any urgent things? I mean, some of you are already actively using our forum. That's nice, and we try to answer that quickly, but maybe we can also discuss a couple of questions here in class, right? Does that make sense? Yeah? Okay. Yeah. So how should I start? So I think I wanted to start with something like, again, the architectural view. Yeah, keep in mind we have this levels of understanding. I try to stick with that. So far I haven't shown you any C++ code. Of course, this has limits when discussing database buffers, when discussing devices. Maybe there's a need to actually use C++. You can't do everything in Python, of course. Memory management. You can't really do that, but still in Python, to a certain degree, you could do that by implementing stuff in Python. It's a library called Cython, actually, that allows you to implement libraries in C++, binary code, and then use them in Python as libraries. So that's the way to go. That's actually what the machine learning people do. So Python has become the language for machine learning and AI these days, but of course, the crunchy algorithms, the CPU-intensive algorithms don't run in pure Python. They run in binary. They use binaries for that, but have Python interfaces. So. Okay, so we're in these levels of understanding, and I showed you slides on use cases of a database system. So in the cloud, we basically had a slide like this. Yes? So you have a layered architecture of a database system. And then you can make a decision, okay, where do you host what? Do you host everything in your basement? That's this on-premise idea, which means all the layers of the application are hosted there. The application, the operating system, physical servers, database systems. It's here hidden under this arrow. Yeah? But then there's the option to outsource it in a way to service providers, cloud providers as a service, and that's typically what's done these days. At least some of the services are outsourced, and that gives you elasticity, it gives you scalability, and often a better reliability. So the claim of these service providers is that, okay, they care about that, they do that 24 hours a day, so maybe they do a better job than yourself. Still, when you use these services, you see that they're failing. We were using one service, I'm not saying the name now, a German, European company, and it had some failures for the backup service we were implementing, and it's pretty nasty, because you would believe that a company that's that big shouldn't have these kind of issues, but they had really issues with that, and now, okay, what do? We think about switching to a different company. But that is easy if you use the interfaces that exist for these cloud providers and don't code your stuff for a specific cloud provider. Yeah? As in all of software engineering, always code against interfaces, not against a specific thing, and then it's easy to switch things. Same here as in the cloud services. Yeah, I don't know what we can do about that. So the different trade-offs of performance we talked about, how to profile a database application, the issues that arise with that, and so forth and so forth. So, okay. Yeah, then we looked at the architecture of a database management system, and that's basically the zoom in that you see of a system like that. So on top there's an application or an ORM or application framework and whatnot that's sending SQL queries down to the database management system layer. So this is a layer. There's an API here. Our API is SQL, of course. And then underneath there's storage, basically key value stores. It could be, the layer could be split into different key value stores, depending on how you configure that, many options for doing so. And then we looked inside the database management system. So we started by developing this versioned key value store that has a list of committed values. So that's always this key value store mapping an object ID to a list of committed values plus one optional work in progress version. That's how we started. And based on that, then we developed MVCC, an MVCC store, extending that store. Based on that, we then later on develop an indexed store. On top of that is a query optimizer. This is software design. The software design is a decorator pattern. So from outside, you might be calling the store directly, but you may enrich the functionality through a query optimizer. We haven't talked about that yet. That will come in January in more depth. And of course, there was query optimization also in the undergrad lecture. So if you attended my undergrad lecture, you saw it at least. But we will have more of that later on. There are many things that are important here. But basically, it means that calls to the API may go directly down to the store, like create index, for instance, or something like that. Or they might be optimized by the query optimizer. And that is actually what happens in a SQL database system. You just send the SQL statement, and the database system may decide to optimize that statement or may decide to, I don't care, right? Well, of course, always the optimizer is triggered for if it's not a prepared statement, at least then it's the query optimizer is called and will try to come up with an optimal plan. But that's the main architecture you will be seeing, and then the question is how to organize these things. I think we can skip that for today. And then we also talked about the different interfaces, also along the lines of code. So, so when you look at textbooks and when you look at our undergrad lecture, there's always this notion that one query is coming in, you optimize the query, you compute the results to the query, and that's kind of weird because that's not what you do in real life. For instance, even if you go downtown Saarbrücken to do shopping, it's not that you go to the supermarket, then you go back home, then you go back downtown to the pharmacy, then you go back home, then you go back downtown, and then you go to another market, and you go. That's stupid, of course. You go downtown, do all the shopping, and then you go back home. So that's a shared shopping in a way, shared shopping cart in a way. Even the shopping cart in the supermarket is an example of a shared scan in a way. So you try not to pay every time the costs for executing a single query, or in this world, in the database world, you try not to scan data for each and every query independently, but try to maybe leverage the I/O costs for multiple queries at the time, or whatever costs you're paying in the system, you try to leverage it for multiple items at the same time. And that has ramifications for the interface of a database system. You could do something like that internally without changing the interface, but you could also offer an interface to the outside user to say, hey, give me your queries rather than one query and optimize them together in a batch. So that's one way to extend an interface. The other is something like this idea that you don't necessarily return a denormalized table. That's standard. So a SQL, where's the slide where motivate the problem? Standard SQL statement will always return a single table. Here's the statement. So no matter what you touch upon, what you list in your from clause, the result will be a table. That's it. That's how SQL was conceived and designed, and that has limitations. So we thought about, okay, what if you returned a sub-database somehow? So a bunch of relations, maybe those relations only having those tuples that would be part in such a single table statement. And that leads to a result, the notion of result DB, that leads to the Anakarkis algorithm that reduces. We had that here. So that's something you want to look at for the exam as well. Basically this bottom-up, top-down reduction of the different relations through semi-joins. Semi-join. What is a semi-join? It computes the tuples that would be part in a join. So typically when people say join, they mean inner join, two relations, tuples are connected, and then you get a denormalized output. Here it's about finding out which tuples from one relation take part in the join of the other relation. So if I apply the first step here again that's a relational algebra notation. It's basically like the inner join then projected back to the attributes from one of the inputs. Again, keep in mind that this is set semantics, duplicates are removed. In other words, this means, okay, we only get those tuples from R that are part of the join result with S. It's kind of simulating a join. It's kind of saying, if I joined R with S, which tuples would take part in that join? So it feels more like a filter operation, the semi-join. Yeah. But it's super useful for these kind of things, and there's many applications also in distributed systems and whatnot. So it's a long story behind that. Yeah, what else can I say? Yeah, we talked about indexing. So that's basically the extension to this graph then. So we said, okay, now we add another layer. That's again extending the MBCC store, adding support for indexes. You can create and drop indexes, and then you have to maintain indexes. So the focus here really in the lectures so far was on, okay, what the heck? Now I do updates, deletes and stuff to my store. Oh, I better be careful that the indexes know about that. That's index maintenance. The index have to be maintained. You update something, the index has to know about that. The specific trick here you have to understand is really the index does not return the precise result. It only returns the object ID that might have a result. So it returns a superset. Yeah? So I use the indexes in my implement. You can do it differently. Yeah? I use it like to return the object IDs that may have a result to your query. If you say, okay, give me everything where A equals 42, and then use the index for that to look up the stuff, it could be that there's already a new version where A equals 43, but if some of the old versions was 42, that will still be returned. Yeah? So you get basically the object IDs, and then based on that, we will later on in January use it for query processing, and that means we still, for all of these object IDs, we have to call the version this method that determines a snapshot that's seen by this transaction. Yeah, that's important. It's not just returning all of the lists, but really saying, okay, this was a query issued by transaction 42. So what is this transaction allowed to see? But we will look at that in more depth. In January here, important is to understand how to maintain those indexes. Yeah, there was one question, maybe I can briefly talk about that. In the forum, I changed that yesterday. I didn't commit it yet because one of my PhD students told me that would confuse you, but I'm showing it to you here anyway. I hope to clarify things. So I don't merge it in domain, so I'll do it after the exam. But basically, we had these version entries. So on the left, you see what you see on main. And we had this version entry. That's one of these entries in these committed lists, or the work in progress entry in this versioned key value store. That's of type version entry. And it was a bit hacky in the sense that there was this flag saying, okay, you could set that to true, and that would mark that this entry was deleted. The value was deleted. Yeah? So basically, a transaction would say at validation time, okay, that is from this point in time onwards, this object ID value was deleted. And then you could, what the heck is the meaning of value in that world? It doesn't mean anything because it's deleted anyway. Yeah? So I split that up a little bit into a hierarchy, and now I have an abstract version entry. It has a start validity, and we have two subclasses. One is an update entry, which actually has a value object, and the other is just a delete entry marker. There's no fields whatsoever. This is just marking, okay, starting, so this will inherit everything from the parent class. Yeah, so the delete entry has a start validity. And that means, okay, if you enter something like that into the store, then that marks a delete, but it doesn't repeat the value again because it doesn't make any sense. Yeah? That's basically the change. I can also merge it today. I'm not sure whether that helps, but I don't know, my PhD students said, no, don't confuse the students, don't merge opinions, don't do it. Yeah? But I think, anyway, I think it helps clarify the semantics. That's what I had in mind. It was a bit hacky here. I think now on the right, that's how you should do it. Okay, right. So that's where we were. So we have these indexes. We talked about index maintenance, how to do that. Right. So I'm not going through the code today. Yeah, then B trees, of course. B trees, again, keep in mind the motivation. It's insanely versatile. Yeah, back then we didn't have the notion of the store, but the main trick for B trees, why they work so well, is that the nodes can be mapped to these storage units. We had these pages, a 4K page. We had a cache line being whatever, 64 bytes or something like that. You just map nodes to that. You just say, okay, my cache line is one node in my tree, or my page is one node in my tree. And you set the parameters according to that. And then it works super well in the storage hierarchy. That's the only trick you need to play. Yeah? And then you can do more tricks to make it cache oblivious and whatnot. Yeah? But that's the reason why B trees map so well. In contrast to binary trees, binary search trees, they have these tiny nodes, and it's very hard to map them to the storage hierarchy. Yeah. So that's one of the reasons why database people love B trees. Yeah, and you have all kinds of extensions, improvements, and whatnot. Can be adapted in crazy ways. And it's still one of the most important index structures. So when you look at database systems, those are the structures you see. So B trees, of course, hash tables, super important. Again, hash table has this problem that you can only do point queries and not range queries. There are tricks to extend hash tables to also support range queries, like order preserving hashing. We didn't tackle that. For the context of this lecture, it's important to understand, yeah, hash tables, point queries, B trees, point queries, and range queries. Yeah, that's a super important distinction also when using any database system. Yeah, more recently, radix trees and tries were used. We will tackle that in that 1 week from now in this Christmas lecture. I will present the radix tree, not the compressed variants. They're now used. DuckDB, for instance, uses artful indexing. Yeah, and bitmaps I will tackle next week on Wednesday. That's also a super important, great technique for database systems, in particular read-only database systems. Yeah, then we had this notion of nodes and leaves, of course, and this textbook style constraints, and then I got rid of those constraints. So this minimal fill grade, yeah, I think we assume it in the assignments typically, but in a real implementation, you can soften that and say, okay, there's some underflow in the node, whatnot, who cares, yeah? Many implementations do that. And then you come up with, okay, what you have is, it's not a B tree in the strict sense of a textbook B tree or of the papers proposing it, but it's an n-ary tree, yeah, where the internal nodes or inner nodes have, a number of keys, yeah. So it's basically n capacity is the number of keys, and n capacity plus 1 is the number of pointers. You always have one pointer more than keys. There's no values in the inner nodes. And then you have leaves. Yeah, and the leaves are key value stores again, of course. And this is a mapping from a key to a value. Leaves are also connected in a linked list. This is used for range queries. Yeah, this ISAM range query property. And your B tree implementation must maintain these things. Yeah, we also looked at that at length in the implementation. Yeah, for the terminology, just keep in mind when I say B tree, I mean B plus tree. So there's a couple of variants there, but the overall main structure is always the same. It's details. Okay, we do this constraint and that constraint, but it's more or less the same data structure. Yeah, we looked at examples for that. I think we don't have to repeat that. Again, any subtree is a valid B tree. That's important to understand. Any subtree partitions the data space into disjoint regions. So if the entire B tree covers the entire domain, so by introducing a root node, you split it up into 3 regions. You have to make a decision where to include the boundary. So here 43 goes to the middle region, 43 here is excluded, so it's a fully open interval, and so forth. Yeah? If you allow for 43 being inserted as well here and there, you will get into trouble, unless you fix your point query algorithms. But the goal is typically in these trees to, okay, there's one subtree I run down in any operation and not multiple of them. There are trees, of course, that do it differently, but the B trees we talk about in this lecture are only one subtree. Yeah, and so forth recursively. Yeah, what else can I say? And then the split, of course, we talked about that at length, how to split these. That's the split. The main thing to keep in mind is the split will never change the balancing property of the tree. Yeah? So it's basically makes the tree grow to the right. You add a node/leaf on that layer. Yeah, that's what's happening. And the only way for a B tree to grow in size is if you split the root node. If you split the root node, you add a layer on top. Yeah? So the root node is replaced by two nodes, yeah, and one new root node on top. That's how you grow a B tree. Yeah? By splitting in terms of the number of layers. So, yeah, I've looked at. I also have the same example as the notebook. So I didn't show this one. Yeah, this is from the BDE lecture. That is basically mapping a B tree style index to file system. But I think we didn't talk about that. Yeah. Why did I show it again? It's included. Okay, then recursive model indexes. So the core idea, the core idea is that I also prepared that in this one notebook where I showed. We had this one more a bit fancy notebook where I took the B tree and then replaced the leaf level to count and stuff like that. Yeah.
How familiar should we be with like more complex cases of deletion in a B tree? Because we didn't have any of that in the assignments sheet.
Yeah, then I don't think you have to. We can again double check with the exam. I can double check with the exam because the exam is set carved in stone, but I don't think. So it's obviously inverse. Yeah. So if you split, the inverse operation is a merge. Yeah? And if you delete, what you can trigger is not splits but merges, of course. If you have this constraint that the node/leaf must not underflow, yeah, you could also implement the delete and say, I don't care, right? Yeah. But it's relatively easy. Yeah. If you understand insert and split, that's just the inverse. Yeah.
So if in delete process we delete something, but the key was a part of the reference up in the node.
Doesn't matter.
It stays
there. The only thing is that you keep all the invariants in the tree. Yeah, invariants meaning, so these are, it's like a street sign that's directing the search. So it doesn't matter whether this is a key that actually exists down there on the leaf level, it just has to point you in the right direction. So no matter how you implement it, as long as for each and every possible search in the tree, you're pointed in the right direction, it doesn't matter. Yeah, that's basically the constraint here. Yeah, other B-tree questions? Yeah?
Why are the leaves marked with the stars?
Why are the leaves marked with a star? That's an interesting question. Maybe it's to differentiate the stuff that exists already from the stuff I'm inserting. Yeah. So 50, the new values don't get a star. Yeah, that's the leftover from some older visualization. You see the new numbers don't get a star, the old numbers, which just differentiate new and old values. I just reverse engineered that, right? I don't know. Probably that's the reason. Yeah.
When I was like looking up stuff about B trees recently, I found that usually they mark it with stars because it's not only the number, but it also contains the data itself, and the star is just a mark. It's not only the key, but.
So. Yeah, sure, that could be something like that. Yeah, so again, the value may be of any type. Yeah, so here the value is an integer. Yeah, but this could also be a placeholder for a pointer to a tuple in the store, object ID. Yeah, Or you could put the object ID here, whatever the value is of object ID. We used strings in the implementation. Or you directly put a pointer to this list in the version store with the committed entries. That's also something you could do. Yeah? That's up to you. So what you store here may be anything. In a typical database, what you store here is called a row ID. Row, R-O-W-I-D. So the ID of a row, that's a unique key to a row in the store. But it's very similar to what we use, like an object ID. It's a unique key allowing you to identify the store. Actually, I think Microsoft SQL Server uses primary keys here. So if you create an index on database table, you don't keep the row ID. At least in some version they did that. They keep primary keys, and then you still use the primary key index to look up the stuff. So many, many options here. Okay. How did we get to recursive model indexes? Because we had this notebook showing so these internal nodes are kind of a statistic of the underlying data. They give you kind of a histogram or a distribution of the underlying data. And already the root node does that by partitioning the data into a couple of subtrees, and recursively you refine those statistics. And I had this notebook where I replaced the actual leaves by counting leaves. And then you saw that it generated an acri-def partitioning. So the internal nodes are a model of the data. They model the data and basically allow you to update stuff through or to look up stuff through the model. And this same idea is used in recursive model indexes. So this index is a model. And the model they're using here is typically a linear function, a simple linear regression, pointing you in the direction of where the data resides in this array. And of course, the model is imprecise, so you have to post-correct in a way. So the index gives you a region. It keeps the different ways how to keep errors in such an index. Basically, it tells you, it's probably there, at most 10 to the left, at most 12 to the right, and something like that. And then you somehow have to post-filter the stuff. So this is another example of a filter index in a way. So the regression points you somewhere, gives you not the precise result, but a superset, and now you have to crack down the superset to the actual result. Maybe there's even the key you're looking for is not even there. Could be the case. And actually, you can play similar games with B-trees. I think we didn't do this in this iteration of the lecture. I don't want to. Maybe we can do that later if time allows for that. Right. Then there are different training algorithms and the trade-offs and stuff, but we can do this in the Q&A. Marcel will also join us later on in the second part if you have more detailed questions on that. Then we talked about storage. So this main idea of a storage hierarchy, what it means if you split up layers, that you split up in particular the hard disk / SSD layer, but I think, what should I repeat? How much time is left? Of course, maybe one of the most important things are this random versus sequential, this experiment, and how random access doesn't really improve, at least for hard disks. Sequential read improved a lot over the years. Nowadays, hard disks are not used for real production systems anymore, or should not be used. You should be using SSDs because random I/O is so much faster, at least a factor 100 or more you get from an SSD. And an important property of SSDs is really that you don't have only one thread, one disk arm executing random I/Os, but you can, on an SSD, you can execute multiple random I/Os in parallel. That gives you another factor in terms of the number of I/O requests you can process at a time. So SSDs is always the stuff you should use for a database system for storage. Right, and then of course we talked about RAID. So that's a super important technique. You see it all over the place. And we had these different rate levels. So we have units in terms of blocks or pages. That's a synonym. Again, the terminology is typically we say block. We have a chunk of data, say whatever, 1 kilobyte. And if that chunk of data resides on the storage medium, we say it's a block, on a persistent storage medium. If it's in main memory, which is also a storage medium, but it's not persistent, we say it's a page. That's the terminology in literature, but it denotes the same data. Whether I call it block or page, whether I say block 1 or page 1, it's the same data I'm talking about. And RAID has this, so the idea here really is rather than buying a super duper expensive disk with a lower failure rate and with an insane performance, rather than buying one Ferrari or one expensive Porsche or BMW or whatnot, you buy a couple of Skodas and basically connect them and then hope that these 5 Skodas combined have a better performance. No, it doesn't really work. They're not faster than the Porsche. Bad example. Okay, but yeah, so for this it works. So the idea is sometimes analogies just don't work. Yeah? But so it's boring if you think about analogies ahead of time. Sometimes I do that, but it's more fun and more challenging for me in class. I just have the idea and go for it and see where it leads me. Okay, this was a dead-end street. Yeah? Okay, but you get the message. Yeah? So you have a couple of cheap disks, inexpensive. That's the I in RAID. Redundant array of inexpensive disks, rather than redundant array of expensive disks. You have inexpensive disks, and you don't care that they fail, or you don't care that they're slow, because using RAID, you can read and write stuff in parallel, yeah? Depending on your RAID level, of course. Yeah? And if one of those fails, you don't care because you have all these other disks that may compensate depending on your RAID level. Yeah? It's depending on how you configure that. But that's the main idea. Yeah? So combine a couple of cheap devices to have a much higher reliability and a much higher performance. That's the core idea of RAID. And we had these different levels, striping, no redundancy. If you lose any of the disks, you're screwed. But here, for RAID 0, for instance, you can read in parallel. Yeah, that's fantastic. Double the performance, or of course, you can use more disks than 2. For RAID 1, you have full replication. Still have an advantage with regards to read. You have no advantage with regards to write. You can lose all disks except one. Yeah? So a very high degree of redundancy. So it's not a good trade-off in terms of the space being wasted. So typically what you would use is something like RAID 5. RAID 4 is basically going there. RAID 4 is saying, okay, I use on my first K-1. So here the first 2 disks I use RAID 0, striping, and then you add an extra parity disk through bitwise XOR, which has this nice property that you can always reconstruct B2, for instance, by just XORing the parity with B1, and so forth and so forth. It's really cool, and all the RAID controllers do that automatically. You don't have to do anything. Yeah? But this has a problem that for every time you write to block 1 or block 2, you also have to write to this parity block. This increases the so-called wear of the device. The more you write to a device, the higher the likelihood it fails. Yeah? So you want to spread out the risk that any of the disks failed, and you do that by distributing the parity round robin over your array. Yeah, that's what RAID 5 is about. That's the most important RAID level. Actually, that's something you could use. Yeah, and we played in Python with that. We talked about nested RAID levels. Again, be careful with the naming conventions. So this is the bottom-up convention. 1 means, the leaves are 1, and then the node here is 0. And then you can think about, okay, what are the properties, and so forth and so forth. So, okay. Yeah, we talked about virtual memory. That's relatively important because it hides the physical memory addresses underneath, and that's done through a page table. I showed you a little Python example for that. I think we can skip these for the moment. The copy on write pattern. So this idea that you only copy the stuff that's changed. So if you have 2 transactions, I mean, we actually do that also in MBCC. It's kind of copy on write if you think about that. You have one object ID mapping to a value. So rather than So if one transaction wants to change that, rather than directly writing to the value, you copy the value over to the work in progress entry, and then it's being changed. So no matter, so if the second transaction that is writing screws up that entry, you don't have to worry about it because you still have the committed entry. That's copy on write, yeah? On a per object granularity. Yeah, so much about that. Yeah, and then we embarked into external memory algorithms, in particular external sorting. So again, the trick is to work with the right abstractions. We use the abstraction as a queue. A queue, in the terms of an interface, a queue interface can be backed up, can be implemented by a file, by memory, by the network and whatnot. And if you develop your algorithms that they operate on a queue rather than on a file or on this network device or whatever fancy storage layer, you can reuse the same algorithm for different storage layers. That's an important trick in external memory algorithms, so factor out the stuff that may change or maybe a strategy or parameter. And that's what we did with external sorting. So again, external sorting is really one of the most fundamental algorithms in big data, so to say, because it teaches you so many aspects of how to handle big data sets effectively and efficiently. And yeah, that's why we talked a bit about that. Yeah, it has these phases, these run generation phase. So if you have here, we have 8 pages, each page only having 2 integers. And then the first phase is phase 0 is generating sorted runs. So here I assume I only have these 2 pages available. The overall algorithm needs 3 pages. The merge needs 3 pages, but here for simplicity I say it's only 2. So what I do is I load these 2 pages into my memory, sort it using quicksort, for instance. Yeah? I sort these 2 pages in memory using quicksort, and then I write out, that's the sort, and then I write it out to an output file. This output file is called a run in the context of this algorithm. So it's a sorted sequence of these integers. I do that for the entire input. Yeah? So always load 2 pages. In other words, whatever memory you have in this phase, you fill the memory with data sorted in my memory and write out the run. Yeah? And once you're there, then you can start merging the runs iteratively. Yeah? So you start here, for instance, with these. You only need 3 pages for that. So here I have 3 pages, and for each run, I load the first page from disk into main memory. Yeah, so I'm now explaining it with disk and main memory, but again, it's queues. It can be on the more abstract level, it's queues. Yeah? But if the underlying queue implementation is a file, that is basically what happens. So you have this page loaded, that page loaded, and now you initialize a heap. The heap points you to the next smallest element. Yeah? You keep on drawing from the heap, and you always remove the element with the highest priority, that is the smallest element, the smallest value, and you send it to the output. Yeah? So you reserve one empty output page initially, then you find out, aha, 2 is the smallest, send it there. Aha, 3 is the next smallest, send it there. And then you write out this page to the output run, to the new 4-page output run, and you load the next page from input run 0 in this example, and so forth. Eh? So you step through the input runs and keep on appending to the output run. And you can do that with 3 pages only. That's the cool thing about that. Yeah? No matter how big the data is, 3 pages of memory is enough to sort any file. Yeah, and that you do until you end up with this. So now you have a run which has, of course, double the size as the input because we had 2 input runs. Keep in mind, you would never, I can't imagine a situation where you would only merge two runs at the time. Doesn't make any sense. It should be more than that. That's called the fan-in. Yeah? And of course, there's a theoretical boundary we talked about. If you have m pages, the maximum fan-in is m-1, yeah? Because m-1 pages, 1 page for each input run, 1 page for the output run. Yeah? So that's the maximum fan-in. But in terms of random I/O, that's typically not such a great idea. So the truth is in between 2 and m-1. Yeah? These 2 extremes, we had it on the blackboard. in that lecture as well. That's something, that's a configuration parameter that gives you the highest end-to-end runtime. Yeah, you do that for the other 2-page runs as well, merge them into 4-page runs. Yeah, then you keep on merging this stuff into a final 8-page run. Again, keep in mind, in a real implementation, and in the implementation done in our Python system, you don't have to materialize this stuff into a file. So the 8-page run, you don't have to perform the merge and afterwards tell the user, hey, now I did it. If you are in an iterator model, you can do that demand-driven. Yeah, so the external merge sort operator in our implementation is an iterator. So people use that as for-element in external merge sort operator. They draw the next element. And every time they draw, you can trigger the heap to, hey, give me the next element from those 4-page input runs. In other words, the final merge should be performed online. Yeah, that's an important optimization. And what you gain is you save once writing the file and once reading the file. That may be a lot of I/O. You don't want to do that. So yeah, that's an important thing to do in this algorithm. Yeah, and then we also talked about replacement selection. Replacement selection is a super nice algorithm by Donald Knuth, and it allows you to often generate runs that are bigger than the available main memory. Yeah, so here, if you have 2 pages, the output in a standard quicksort-based external merge sort, here we go. Yeah, so you have these 2-page runs because you had 2 pages of main memory. But if you use external merge sort, not external merge sort, replacement selection, yeah, this is a quicksort variant, but if you use replacement selection, it may look like that. There's no guarantee that it is 4 times bigger, depends on the order of the elements in the input. Yeah, but there are situations, or often if you play with the algorithm, you see, yeah, that's okay, it generates a bigger run. If you have bigger runs, you will have fewer runs. If you have fewer runs, you have a high likelihood that you have fewer merges, or maybe even fewer merge levels. Yeah? So the overall performance will, with high likelihood, increase. So that's a good idea. CPU-wise, replacement selection is a bit more intensive. Yeah, but depending on modern machines, maybe it's a good trade-off. So external merge sort in general is I/O bound or should be I/O bound. Again, it's hard to say whether to always use replacement selection or quicksort. It depends on how you're running it, on which layer of the storage hierarchy are you running the algorithm. Yeah, so you can play with that and do experiments. But the algorithm, so what it does is you have this input in replacement selection, so we're operating from right to left. In its eternal structure, in a C++ implementation, you keep an array here of 4 elements, and parts of the array is used as a heap, the other part is used as a list. Here I depict it as 2 different structures, but just for clarification, but in reality, it's one structure where you have some split point somewhere saying, okay, everything to the left is a heap and everything beyond that is a list. So we start by loading, filling up the main memory, like in quicksort, with 4 elements. We create the heap property, like we sorted here in this visualization. And then we keep on drawing from the heap. And it's important to keep track what was the value of the last element sent to the output. That's the major trick here. So we remove the 10 here, and we record that the last element output was 10. Now if we can load the next element, 25, we check whether this is bigger than the last element output so far. 25 is bigger than 10, so we can simply add it to the heap. It doesn't violate anything, it doesn't ruin anything. Yeah? So I just put it into the heap in the right position. Continue by drawing the smallest element from the heap again, which is 20. Yeah, so now this value here changes to 20. The next element is 73. Oh, that's bigger. Cool. I add it to the heap. I remove 25, send it to the output. Now I'm getting 16. Oh, 16 is smaller than 25, so that would have to be inserted here, but that's already gone, that opportunity. Yeah? So I cannot, that's a queuing model again, I cannot insert in the middle, I just can append, so that would ruin the sorting property, so there's no way I put that to the heap, so I put that into the list. Yes, the heap is now shrinked down to 3 elements, and the list has 1 element, some of it is 4. Now I draw the next element 30, send it to the output. This value changes. I draw 26, again smaller, must be sent to the list. I draw the next element from the heap, that's 40. I'm drawing 33 from the input, again smaller, must be in the list. I draw 50. 50, wait, hold on. 33. Jumping over 50 here. Oh, no, sorry, now I got confused. No, so now the heap has 1 element, the smallest element is 73. I send that to the output, change the value here, and now I draw 50. 50 is strictly greater than 73, so I have to append it to the list. Now the heap is empty. Now I start all over, which means all these elements in the list will form the new heap. So I move them here, establish the heap property. Here it's visualized by sorting, and then I start all over again. In the output, you have to make sure, of course, that you understand the split. So this is run 0, this is run 1. As explained on the blackboard, you can do that through nested iterators. So the replacement selection algorithm would return an iterator of type object type you specified. That's the way to go, and that would make it fully demand-driven. Yeah, that was a tour de force through the material. Okay, let's continue. Just a minor clarification, because someone approached me in the break. So this could be misleading. So what I'm trying to say is I check the predicate whether the number I'm drawing from the input in replacement selection is greater or equal to the number I returned so far. So this is a comparison, the predicate with this last element on the output. And if it's false, this check, I mark it as red. If it's true, the check, I make it as green. But of course, 33 is not greater or equal to 40. Yeah? So that would be false, of course. Yeah? 33 is smaller, 40, obviously. Just, I'm not sure. Maybe I clarify that on the slides. So, as promised, now we do a Q&A. Let's start with ARM-EYES. Marcel is here. I just finished his PhD, maybe just as a footnote. So when you do a PhD, you become the world expert in topic X. So ARM-EYES is the world expert in read-only ARM-EYES now. It doesn't mean that he's a complete, super over-focused expert on that. He also knows other stuff, but he's the guy to ask for ARM-EYES. So if you ever had a daring question about ARM-EYES, now it's the time, or you be calm forever. What is the sentence being said in marriages? Yeah, if anyone is against the marriage, now speak up, or shut up forever. Right? That's the time for ARM-EYES now. Your call.
May we ask you questions that are not related to ARM-EYES?
Yeah, later
afterwards. But I
mean,
mean,
but now because he will leave in a moment.
If there are no questions on ARM-EYES, I'm fine to leave. Lecture was too good or what?
Was too good, right? It's still so excited about it. Right?
Yeah.
Practice, is it used a lot and does it work a lot?
From my experience, it's not used at all currently. It's relatively new. There have been improvements over ARM-EYES already. So there are learned indexes that support updates, that support inserts. And of course, in most cases, you would go for those, even if the performance on lookups is slightly worse. But yeah, that's why they're not really used.
But I mean, at least Amazon acquired this startup, right? And then they're doing.
I mean, the thing with learned indexes is that ARM-EYES basically came up with this idea that you want to have this function that maps keys to positions. And a lot of other learned indexes use the same idea. They're just using other techniques to approximate this function. Yeah.
So this DBIO that's from Carnegie Mellon University lists all the databases. Oh,
Okay, so yeah, Microsoft probably has,
I'm not even sure whether the search is correct. Let's first.
they probably have Alex
That's it.
integrated, which is
Ah,
like,
okay. But it's not recursive, it's just recursive, and then they have model index
yeah,
distributed.
okay, yeah,
it's
but
not phrase,
yeah. So there's a version of a learned index by, that was developed by Microsoft, which is called Alex, and probably they have it integrated in some prototype version of SQL Server, I don't know, but yeah.
They don't even have a category here yet, or it's just for the search result. Yeah. Yeah. So Marcel showed it on one slide only, but if you use it as a replacement for B-trees and hash tables, you won't see the performance from the outside. So it makes a lot of sense to use that inside in operations, but that's always the question how you measure an index. Do you measure it independently, or do you measure it as part of a system, and that you will yield very different performance results.
So the performance numbers that I showed are more on the theoretical side because you continuously query the index over and over again. So this is not really in the context of a system. So in the context of the system, the performance benefits that you may get are much smaller, actually, because you don't have that repetitive pattern of accessing the index. Yeah, so.
Good.
Any other RMI questions? Yes?
Yes. One specific problem that I noticed with RMIs is that you have to fine-tune the RMI for each data set, if I got it correctly. So the question is, I mean, even if there are only a few parameters, then it probably means you have to train the data set on all the combinations of those parameters. Is that so, or?
This was like that, but we actually did hyperparameter analysis where we looked at a large number of configurations, and we found out that in most cases, so the cases where we don't have these extreme outliers that I showed in the lecture, you get away with pretty much the same configuration for all data sets. And this is a relatively simple configuration where you just use a linear spline model in the top layer and then linear regression models in the second layer. And this works very well. And you can then just scale the size of the second layer to whatever suits your preferences or the amount of memory that you have available. And this, in practice, works relatively well. So,
Sorry.
No?
I was trying to ask, even if the data set follows a very strange distribution.
So this is something that I did not go into in the lecture that I gave, but what would you consider a strange data distribution? Because there's an important observation to be made, which is we have this mapping from key to position, and this is always a monotonous function because the keys are sorted, right? So there are only 3 types of strange things that I would say could happen. The first thing is that we might have extreme outliers at the top end of the function, which is what happens in the case where the RMI did not perform well. So then we have like some monotonically increasing function, and then for whatever reason we have these extreme outliers, so we have a flat line at the top, right? Or a relatively flat line at the top. Then the converse of that is we might have these extreme outliers at the beginning of the data set. So we might have a flat line here, and then we have a monotonically increasing function.
So X is the key, like there, right?
Yes, yeah.
Y is the
So
position.
it's again key to position. And then the only thing that we can still have is that the keys might occur in clusters, right? So then we have something like that, where we have something that looks like a step function. So we have something like that, then we have a lot of keys, then something like that, then we have a lot of keys, and so on. Yeah. So these are basically the only 3 hard cases that can occur. Okay, so these 2 cases are the thing that I showed in the lecture, where it doesn't work well with the easy configuration that I just explained. And in this case, it still works reasonably well, because if we have the linear spline to approximate in the first layer, we will get something like that, which is still relatively good. Yeah. Does that answer the question? Okay.
Any last question about RMIs?
What do you do in the other two?
I wouldn't say that you're doomed, but so you don't get away with using these super simple models anymore. So what you can do is, well, which is like a neat trick, we only have very few keys here, yeah? So what we could do is we just ignore them. Yeah, we ignore them when we train the model, use a linear model again, and we have something like that. Or in the other case, something like that. What does that mean? Well, the result of that will be that all those keys that are here, only if these might only be a few, yeah, but all those keys will be assigned to the same model in the next layer. And the approximation of those might be inaccurate depending on how many of the keys at the start of the remainder of the function are also assigned to this model. But for the rest of the keys, it works still very well. But in order to come up with something like that, you either have to guess the amount of outliers that you have, or you have to do some pre-analysis to find it out. So it's not that simple anymore that you can just pick a very simple configuration and run with it.
Okay. I mean, the general thing to understand about recursive model indexes is that they overfit your data. So in the B tree, you don't have to worry about what the statistical properties are. You just create the B tree and it's robust to changes of the statistics. And RMIs, that's not the case. If the statistics change, you have to retrain and recreate the index. Yeah? And by overfitting, you get better performance, but you lose robustness. Yeah, that's a trait. That's the game you're playing here. Huh? Okay, thanks, Marcel.
Yeah.
So at the end, when you get a new data set, you always have to look into the distribution of the data and then decide. It can't be automatic.
I mean, you can automate the process of analyzing the distribution to some extent, but other than that, yeah, you have to do some analysis. I mean, you can use this configuration that I just described and see how it works. And in most cases, it should work very well, but there might be cases where it doesn't. So, and then you have to do some additional analysis, basically. Yeah.
That's a general problem in database systems because basically it's statistics about your data, and the same problem exists in cost-based query optimization that relies on statistics. And if statistics are outdated, the plans generated will be crap. Yeah? So you have to have a mechanism, like you suggested, to understand, oh, my statistics changed, I better collect that. Yeah.
Yeah.
That's yeah. Okay, thanks, Marcel. Yeah. Microphone. If you still have questions, you can go to his office, right? He hates that. Okay. Okay, any other questions? Yeah.
Question relating the indexing. So I wanted to clarify the thing that you mentioned about filter query and how it returns a superset.
Mm-hmm.
In the implementation that we have. Does it has something to do with the fact that we do not provide transaction ID to create when we create index, or not?
So that's two different concerns. So we had this discussion, metadata in the database system. Is that part of transactions, yes or no? And I think I implemented it in the first shot without being part of that. And then there was an exercise asking you, hey, should that be done like that? And no, you shouldn't. Yeah, so everything you do in the database system, creating a table, adding attributes from a table, removing attributes from a table, we don't need it here because we don't have tables, we just have values. Yeah? But creating indexes, keeping track of the information, whether you have an index, yes or no, should be part of a transaction. Yeah, so the fix in the implementation would be whatever internal metadata you keep, you map it to your existing underlying MVCC store and make it part of a transaction, and then it becomes a transaction ID. Yeah, that was the second part of your question. The first part, so that's the filtering property, that the index just gives you the object IDs that may be relevant to your query. Yeah, you still have to, for each object ID, there's this function, I think it's called valid that's already lives here, right? It's register or read snapshot or read object, something like that. We use, and I want to say iterator version, I think. I think one was have to get used to that. Something like that. Yeah. So here's the usage. Here you pass the transaction ID, that is the time and the where clause, and then basically you read the snapshot of this specific version. No, that's the entire snapshot. Sorry, I'm wrong. Get visible. It's this one. Get visible object version. That's basically that's something I will change in January if we want to use indexes for reading. Now, because here you see in the implementation there's a loop somewhere. I know it's specifying the object ID, so you do a direct lookup in the store. So I don't even have to change it. Basically, you get the object IDs that may qualify from the index lookup. Each object ID is fed into this method and will return the visible version that's visible to you. And it might be that the return is none. Then you remove it from the output. Yeah, but that's basically the mapping you still have to do. That's the post-filtering process you're doing here. Does that answer your question?
Yes.
Yeah. It's a relatively easy change to use indexes for reading. Just make sure you map everything to a call to that method. Yeah. Other questions? Yeah.
Question regarding grade 4.
Yeah. Let me first open the slide. Maybe that's the easiest, and then it's also easier to explain for you, maybe. Unaided storage, of course, grade 4. Here?
Yes. So the definition is you have to have at least 3 disks.
Yeah.
How would it look like with 4 disks? Would we XOR E1, E2, E3 into the 4?
Yes, it's always, if you have, so if you have 4 disks, 0, 1, 2, 3, we can rate 4. Yeah, and then there's, how did I start numbering with block 1, right? So you have block 1, block 2, block 3. And this is a parity computed over block 1 and block 2 and block 3. And then I invite you to take a look at the Python implementation, because they actually get directly this output. You see parity over that. I think I have it with this bitwise XOR operation. Something like that is being B2 head B3. That's a parity, and then if you lose anything, you just XOR it with a missing disk and you're back in business. Yeah? Okay. Other questions? No, it's the last row, you.
Yeah, for RAID 10 and 01, are there specific instances where one should compare the other, like in terms of robustness? What would
It's more a philosophical question. Also depends on whether those leaf levels are subsystems. I mean, at the end of the, I think probably I mean, here it doesn't make sense because it's basically just swapping the both internal columns, right? I think what happens if you add more devices? Maybe there you can make a difference. Actually, the answer is I don't know. I need to think about that. But when you Google for that, you also see that there are discussions even for 3 layers of RAIDs. Yeah, then philosophical discussions how to configure that, how to map it to hardware RAID and software RAID, blah 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 blah. Yeah. So I personally haven't ever seen any of these nested RAID systems. It's typically RAID 5 and that's it. And there's an extra backup service. Here goes my replication. That's fine. Yeah, but some people claim they're using this. Yeah, I don't know. Hard to say. I don't know. That's the answer. And if I say I don't know, it's probably not in the exam, right? Next question. There was someone else there, right? Okay.
We have a question about B+ trees.
Uh-huh. We had that before, right? So the star don't mean anything here in this visualization. It just means that's an existing value, and all the values I'm inserting in the example don't get a star to differentiate them from the older values. It doesn't mean anything. In general, the values you insert may be of any type, maybe pointers to a row in the store, for instance, in our implementation, maybe an object ID or a primary key value, whatever. Yeah? No, that doesn't. It's just to differentiate them from the keys. Here's a 50, just to make sure that's a new value, right? And then keep track in the insert sequence. Those are all new values. There's no other meaning. Other questions? Yeah? Yeah? Now, bottom up, assume you want to read all of the blocks B1 through B4. So on this disk, you would be reading B1, B2, and this here B3, B4, and so forth. So each disk reads one chunk in parallel. Yeah, for 3 disks, yeah, the first third of the blocks on that disk, the second third on the middle disk, the last third on the third disk. Yeah, so if you read all of them in parallel, you don't get anything, of course. If you start from the beginning, I mean, it doesn't help, sure. Yeah. 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 So no, I couldn't answer it, so you ask again. Thanks for that. Just kidding. No, come on. 1, 0.
Could you build something like this with other rates?
With what?
With other rates, like a rate 4, 0.
Yeah, of course. So this is with 4, 0. So the way to see that is those are just subsystems. Yeah, so this, you can always, basically like in trees again. So a rate system is just saying, I'm assigning this to a subsystem. And how you organize a subsystem is completely up to you. In this case, the subsystem happens to be a disk, but that could be, you could even do a rate array over rate arrays. Right? If the subsystem here is not a disk, yeah, maybe here if it doesn't make too much sense for RAID 1, but you were asking for RAID 4, for instance. So the only thing you need to replace, rather than having, so this is my disk. RAID 4, so we need a third disk, whatever. So this is RAID 4. Oh, it gets messy a bit. And I have blocks 1 and 2, block 2, block 3, and so forth, parity, whatnot. Yeah, and I'm just saying there's a subsystem that stores this block somehow. And now I'm saying I get rid of this. I have to take a picture before removing it. I don't take a picture of myself. Okay. So get rid of this and say, okay, this now is a data center. Data center being that's a data center in whatever, a different city that organizes my block, right? It's just one type of subsystem, again, one type of key value store, if you wish, that makes sure that the contents of block 1 are somehow stored. It has to have at least one copy of the block, but internally it may be anything. You also see that in SSDs. SSD, if you put it into your machine, it's I had a picture of that somewhere. Here. Yeah, so basically it looks like a hard disk from the outside, solid state disk, and it sits at the same interface, whatever that is, as SATA or something like that. But internally, it has these chips for storage. And guess what? The chips are connected by RAID 5. Internally. You don't have to know about that. Why would you have to know about that? Yeah? So there's some RAID 5 mechanism there doing that. Even in main memory, these, I think it's called ECC or something like that. They have checksums on the DRAM and stuff, yeah, and RAID style kind of correction and stuff. Yeah? You can do that and on any storage layer, it doesn't matter. You do it internally. Yeah? And here on solid state disks are a prime example where basically this device internally, no matter which block you assign, has RAID 5 inside. Yeah? So we're using nested levels actually anyway, no matter what you do. Yeah? Yeah, and that also is then, that's what I meant when there was this first question about this RAID 1 versus RAID 0. That's the system view on that. Yeah? This is basically the white box view of a system. Yeah? So you have these storage layers and you have different layers doing kind of RAID stuff with the blocks. But the question is whether you have access to the information. Do you have access to the information that your SSD does RAID 5 internally? If not, you must handle it as a black box, yeah? And then configure the RAID level according without knowing about that. But if you have a white box information and know what the different devices are doing, maybe you can make a more informed decision about which RAID level to pick. That's the problem. Yeah? So it's maybe you need to read the manuals or tech specs for the devices. Yeah, is that clarified? Okay. No, I don't think so. That's more historical thing. That's basically okay. RAID 1, yeah, nice performance for reads, for write. It's really bad. You have so much degree of redundancy. Yeah, but how do you really scale this up? So if you have 10 disks, you just have 1/10 of the space. It's a super high overhead. Yes, you kind of want to have a good trade-off of reliability and performance. Yeah, so. Yeah, you do have some sort of checksumming. Okay, we put it on an extra disk. That's more a historic thing to do. And then, yeah, you could see in those configurations, oh, this disk would fail very, very often because you would be writing much more to this disk than the other disks. Okay, let's spread it out over all of the disks. Let's do something like that. Yeah? No one uses RAID 4. You should use RAID 5. Yeah? That's even RAID 6, which can survive two disk failures. But then you need a different type of checksumming algorithm. Yeah?
So in the beginning we had the transactional thing, and I was wondering, so we always aborted if we had like a conflict between transactions. First of all, is there like a different solution to maybe, I would imagine a lot of transactions coming in and all of them get aborted all the time.
No, I think I said it at some point. So this is a simplification for this Python implementation because the Python implementation is not really multi-threaded. There's no logs or whatsoever. It's just explaining the principles. You can still have transactions even though you're not multi-threaded. You just have one action at a time. Yeah? And now your situation is, okay, now you have a conflict, say you want to write to something where there already is this VIP entry, what can you do? Well, in a real implementation, you would suspend the thread, the transaction. Yeah? It has to wait. And that's how we do it in the undergrad lecture. So this transaction has to wait for the other to finish and to decide whether it will commit or abort and stuff like that. Yeah? It's very extreme to abort for every conflict. It's a simplification. Yeah. Yeah.
Then maybe also makes sense to limit the size of a transaction. So if you like have a very, very long transaction,
What do you mean by size? In runtime or in?
In like actions, they basically
Yeah.
have two read actions, two write actions at maximum, and it has to be.
Yeah, why not? I mean, the underlying observation is the more you change, the higher the likelihood that there will be a conflict with someone else, which may lead to this transaction being aborted or the other transactions running into problems. Yeah, and then you could say, okay, no, each transaction is only allowed to do X, Y, Z, because then you lower that probability. So that's the intuition, kind of, right? Yeah. I mean, I'm not aware of any active tuning knobs that you can set. I mean, of course, it happens. Assume situations where you whatever for an entire table, yeah, for each row you change the value to b+1 of the old value or something. That's exactly the situation which will tear down everybody who's also on that table. Yeah? So database mechanism per se, I'm not aware of. I mean, there's this notion of long running and short running transactions. That's maybe more important in that space. So long running transaction means it's a transaction that's triggered by UI. You send a begin transaction from the UI. The user looks at it, but there's no commit. So it really depends when the user is finished drinking coffee and being back to their laptop and stuff like that to say, yeah, save, and then the commit is being sent like half an hour later. So the transaction is kept open like forever. Yeah, these transactions are problematic for a database. So there's the opposite is short-running transactions. That is basically when you do something on the UI, the transaction is only formed once you hit save. And there's no begin transaction before, but only it's a point in time. Yeah? And so the transaction is a very short-running thing. Yeah? And that also lowers the potential for conflicts. Yeah? Yeah, because these work-in-progress versions are not kept for such a long time. Yeah? Assume a long-running transaction creating a work-in-progress version on object 42, and everybody else is blocked. No one else can touch the stuff. Yeah? That's a problem. Yeah. Other questions?
Some systems do, like when you're on checkout, you have 15 minutes for checkout. Does it have something to do with
You mean in the shop or something like that?
When you are allowed to.
Yeah, it's kind of on a higher level. Actually, we looked into that in a bachelor's thesis recently. So you're on a web shop, you're checking out some item, and then sometimes there's a timer running down. And then the question is, what does it even mean? Do they now reserve the item for you for 15 minutes or not? Yeah, is there a database stuff involved in the background? Is it just to create an artificial time pressure? I mean, you know this from a device, but only today, yeah, buy within the next 30 minutes. Yeah, which is the oldest marketing trick in the world. Yes, it's basically an artificial scarcity of an item. We only have 5 items left in stock. Yeah, it can be anything. It depends on how they implement it. Yeah, hard to say. Other questions? No, everything clear? Yeah. Well, let me first open the slide. Grade 5, yeah? Yeah.
So, for example, if I have many disks, eventually I have a possibility of at least 2 failing. So,
If it's 2 failing, you're screwed with RAID 5. You need a different RAID level.
right, but if I want to use a lot of disks,
If you want to use what?
a lot of disks,
Mm-hmm.
right? So, I have 10, for example, it is naturally more probable that at least 2 fail.
Yes, yeah, right. That is a point in space in time where you could, for instance, do 2 RAID 5s connected in a RAID 1 configuration. It doesn't have to be 0, 1, or 1, 0 or something like that. You can also use RAID 5 at the, on the bottom and then connect them in a RAID 1. Yeah, so basically each subsystem is independent and still each subsystem can lose a disk. Yeah. That's what you could do. You could have RAID 6 over all of that in a flat configuration. Again, that can survive 2 disk failures. It's a bit more expensive, these checksums they use. But that's basically what you then have to do on a piece of paper and say, okay, I have 500 disks. What do I do? What kind of performance characteristics do I want to support? How many disks do I want to be able to survive if they fail? Yeah, what could be likelihoods, depending on how many disks are used for checksumming and stuff like that, that might have an influence. Yeah? So here I'm spreading out. In RAID 5, I spread out the write where, but still, you touch any block, you want to write logically, conceptually to any block, you always touch 2 disks. Yeah? So it's a higher write where you're creating in a RAID 5 configuration. This is being touched and that's being touched. And then basically, when you have more disks, you have to find out, okay, what do I want to be able to survive in my system? What are the performance characteristics and how do I maximize these 2 numbers? Depends on what these characteristics are and what you want to support. But I would probably go for RAID 5 nested first thing. Yeah. Other questions? No? Okay, then good luck for the exam. See you on Wednesday latest.